And you are live. Rich, you're live, sir.
Well, everybody, this is Rich Russel. I'm the science lead for the Deep Space Exploration Society here in Colorado Springs, Colorado. Our charter is to do long-range communications, radio astronomy, and education. We're composed of mostly ham radio operators. We've got a lot of the radio engineers in town that do most of your AM and FM stations. And we do a lot of Earth moon bounce, which is moon bounce communications, where they can actually transmit to the moon and receive back. So we're geared for all that, advanced communications options. You can see on the lower right is our dish. It's a 60-foot dish, which is in Haswell, Colorado. We obtained that about 10 years ago and been refurbishing it ever since. Okay, what I'm going to do is give a short history of radio astronomy, sort of the highlights of what we've been doing at the Deep Space Exploration Society, and some of the accomplishments that we have done. We've just successfully done pulsar astronomy, and as of actually this weekend, we've just successfully done moon bounce in tropospheric transmissions. Well, first, what is radio astronomy? Well, Carl Jansky, about 80 years ago, was studying what different interferences were happening on some of the radio projects that he was working on for Bell Labs. And he came up and found different signals coming that he could not explain from coming from Earth. And he basically determined that this was from objects in space. He used an antenna. This is his antenna, and actually a duplicate is at Green Bank, West Virginia, where the Green Bank telescope, one of the largest telescopes on Earth, is. He made this antenna, and he basically has wheels on the bottom, so you can rotate it around to see where the different angles were, where the radio signals were coming from. And he was able to determine that there were radio signals coming from space. Not long afterwards, about 1938, Grote Reber made his own first big dish antenna, and this is his antenna. And it's a 31-foot parabolic dish. We'll go into that in a little while. And he was able to map out different objects in the sky and determine that there's different signal levels all throughout the sky. Long afterwards, they've determined that there's such a thing as interferometry. Now, interferometry is like when you drop two stones in a pond and the waves start interfering with each other. This happens with radio waves too, and if you put two antennas far from each other, they will interfere, and actually some of the waves will actually amplify, some will detract. And the use of this amplification was enabled radio astronomers with big dish areas to look to very small objects in the sky. So we'll see some of the big interferometers. I got a picture of those and some of the results from those interferometers. Examples of a parabolic dish. Now, a parabolic dish is anywhere a signal comes in, it'll actually bounce to a center point above it. So you'll see an example of the bounce coming down, and then it reflects back to a central point. Well, there's different kinds of dishes that everybody uses. Our 60-foot dish that we use is a prime focus dish, our 60-foot dish that I showed you. About 15 years ago, a benefactor Paul Plishner donated about 11 acres of land and the 60-foot dish, and by the way, a bunker that he had bought to our organization. And at that time, that there was no power, there was no the motors weren't working, nothing was working at all on the dish or any of the equipment. So these guys for the last 15 years have been refurbishing this dish. They even brought in a van to act as our communication center, and they also outfitted the bunker, which is about 20 feet underground, that was on the property as sort of our social area. This is our dish, and you can see in the foreground is our communications trailer that they brought in. And you can tell we are out in the boonies here. We were out in the middle of cornfields. If you call this corn, this is sort of like industrial corn they use for livestock. So it only gets about 2 feet high. But this is our dish. This is the feeds up here on top. This is our 60-foot diameter. And then there's down here's our communications trailer. And there's underground cables that go between these two here. And actually on this side here, this is where we get up. We actually move the dish down, and we can actually go and change that feed out using this platform here. We've outfitted this dish with many feeds. In other words, a feed is what actually receives the signal and turns it into radio frequency data that then gets piped down to the communications trailer into a receiver and turned into digital bits. So we've been able to outfit this thing with a 400, and in fact, right now we've got a 1.2 gigahertz feed on there. Just as a reference, your Wi-Fi signal is about 2.5 gigahertz, and there's a 5 gigahertz version of that. Your microwave's around 2 gigahertz. So we're around the microwave areas and a little below. 60-foot dish diameter, and there's a whole bunch of information there. This thing probably cannot track a low Earth orbit satellite, so it probably wouldn't be any good for the little small sats, but it can definitely track the large satellites on its. And we right now are tracking astronomical units or astronomical objects. This is our feed. We actually swapped that out with many different kinds of feeds. But you can see the guys get up on top of that platform, and they can swap the feed out right there. And that's those big pipes there are what hold that up. So it sort of gives you a perspective of how large this thing really is. There's our comm trailer, and there's our dish right behind it. This is the inside of the communications trailer. We have receivers set up over here, and we actually control the dish with a control system. It's right here. We spent many nights in here on a bunk in the middle of winter and with heaters on, and it's very fun. But we're sort of like the Discovery Channel radio astronomy group. That we started off, didn't know what we were doing, and then we've become very expert at various things since then. Our bunker. Well, the bunker is right there, and this is what happens in the winter and the summer when we're not there. Is that all these tumbleweeds from the fields get in there, and we have to clear them out every year. And then there's our door to the bunker. This is the inside of the bunker. It's pretty spacious. It's held up. There's about 5 feet of dirt above these things. We've actually got right about here. We've actually got a spiral staircase, so we can actually go up the surface, and then down that hall is where this door is. So we got a lot of room down there. A lot of people spend the night. It's always about 60 degrees in the winter or the summer, so it's a very nice, very pleasant place to be. And you can see in the background, the dish is about 20 yards from there. We also run a ham radio station, K0PRT, and we do moonbounds, tropospheric communications, all advanced ham radio communications, and we set up our ham radio stuff. It's interesting. This picture here This is the Milky Way. And there's Denver, Colorado Springs, and Pueblo. There are the lights there with our dish, and there's a meteorite right there. So it gets very dark there. There's no, we don't have any interference. There's no big towns next to us. And so we got a lot of good, it's a great place to be for not only astronomy, but ham radio astronomy. One of the key aspects of the club is to look at all the different kind of radio astronomy experiments that are being used, so we can show them and have learning experiences with those. One is the SuperSID system. SuperSID is actually this little box here and this antenna, and this goes about 27 kilohertz and produces a nice spectrum like this. And the way this works is that the submarines, there's submarine transmission stations all over the planet that are transmitting to submarines at about 27 kilohertz. And this picks it up as the transmission bounces from off the ionosphere, and this picks it up. And depending on the signal strength is depending on where the ionosphere is either going down or up. Now, when a solar flare hits the ionosphere, it drops the ionosphere, and the reflection becomes very sharp, which gives a beautiful spike on our SuperSID system here. So what we're doing with this simple system, which costs about 30 or 40 bucks, we are seeing all the solar flares that are happening. For a very simple system you can have on your own computer and at your house. Very simple. In fact, I put this is in my house, and I put that together in about an hour, and that is a little can. It's about this big. And that's simple software, and then you're up online. Now you're detecting solar flares. A little bigger is we've established a 9-foot dish, and we're detecting hydrogen, galactic hydrogen. And we were able to tell if we've, by when the Earth turns around, it hits different parts of the sky, and this thing will pick up different hydrogen signals, and we can determine if there's hydrogen signals in that direction. And hydrogen is, we'll go over that, but basically we receive it at 1420.406 megahertz, and it's caused by a hydrogen electron flipping, and in a long distance away, there's so much of it that it produces a steady signal of 1420.406. And what will happen is that by the time it reaches the Earth is moving toward it, or it's moving toward us or away from us, and we can pick up the Doppler effect of it coming to or from us. And from that, we can come up with a lot of information about the interstellar object. And I'll show you some results we've got in a few more slides. Another one that is a really nice project and is Radio Jupiter. Radio Jupiter is based on the moon of Jupiter, Io, rotating around Jupiter. And Io is the closest moon to Jupiter, and it's volcanic. And it actually spews out dust and particles in its wake as it goes around Jupiter. And as it goes around, it interferes with Jupiter's electromagnetic field. And that causes a big spike in the electromagnetic field, which we can detect on Earth. And this Radio Jupiter Pro, which you can get at this location here, you can actually see where it has a detection area in these dark areas, and here's where Jupiter is right here. It'll actually say here's where we predict where Io is going to be in the right spot to produce this burst of electromagnetic data, and then we can receive it here on Earth. So this is a great project for grade school and high school people to be able to look at radio astronomy that's being caused by Jupiter and a movement of a moon around Jupiter. So very fun. We do have open houses, so we invite once a year. Well, this year, obviously, we didn't, but every year we invite people. We get 30 or 40 people to the site, and they get to do telescopes, and we do radio astronomy there, and we do all sorts of cool things while we're doing the open house. We do also have community outreach at the different, Eads is the closest town there, biggest next to Haswell, and we do stop by there and show them what we're doing. The goal here is that this site is near these towns, and they enjoy having the site there, and they sort of take care of it when we're not there. Some other science. This is in the communications trailer, or ops trailer, and there's me sitting there actually trying to detect pulsars right at the moment. We do set up the systems and start detecting pulsars or hydrogen, depending on the project. And we can spend nights there. We can spend the night and do everything in the evening and really get good results. We do track. One of the key things is that we build our own software to track the different objects in the sky. This is a system that tells us where our antenna is pointing. And right ascension declination, think of that as your GPS coordinates for sky objects and celestial coordinates. And it'll actually show you where you are. And here's an example of where the antenna was pointed, sort of like a little road map. And it'll always tell us where we're pointed at a different object. So we can sit there and track a certain object for as long as we want. And that really helps, when we get their data, that we know exactly where we're looking at. This is a little small, but there's different hydrogen readings. Hydrogen looks like a spike, and depending on where the spike happens, it'll be shifted from left to right, and that'll tell me whether it's the object in the Earth is closing or the object in the Earth is opening. Or if it's at zero, that means that they're sort of steady state with each other. One of the projects was to sit there and take all this information and come up and see if we can determine where the Earth is in the Milky Way. This particular one says that, hey, I can also determine where the Earth is in the sun's orbit by where just the Doppler change in the Earth's in the signal. It'll tell me that, after successful measurements, I'm sitting there saying that the Earth's right here and it was over here about 3 months ago. And so we can watch the Earth go around the sun using just the radio astronomy. This is a little hard. This is the measuring the rotation rate of the Milky Way. So the Milky Way is actually rotating, and we're in there with it. And by measuring the different hydrogen regions, you can actually determine that the Milky Way is going about 220 kilometers per second is the rotation of the Milky Way where the Earth is. So that's a really cool example of something we can just get by receiving radio signals. When you know that, by the way, a little math, and I'm not expecting you guys to memorize this or anything, but there will be a test after this. You can actually determine that the mass of the Earth, the mass of the Milky Way inside where the Earth is 1 times 10 to the 11th times the mass of the sun. So from the little data we're doing from amateur radio hydrogen measurements, we are determining the mass of the Milky Way. This became very important because this is one of the approaches they used when they were doing the same thing with distant galaxies. They determined from this that there's dark matter out there because there's not enough light from the stars, not enough star mass to produce this size of an answer on different other galaxies. So from that, they determined that there's something else besides stuff we can see, and they called it dark matter. So this is the same thing that help predict dark matter. And this is also from my little backyard thing. We can detect the signal from the Milky Way. This is all, by the way, in Excel, so very simple stuff. And this is the signal strength of each of those peaks. And I basically plotted those off. And based on that, you can say, here's where the Milky Way is. Because the Milky Way has the strongest hydrogen measurements. And by the way, this is right ascension and declination. So declination is up, down. Right ascension is sort of the passing of time over the, and this shows you where the Milky Way was. And if I shift that to galactic coordinates, so galactic coordinates is that I've got galactic latitude, which is up, down in the galaxy, and longitude, which is side to side in the galaxy. I can shift the same data, but I can shift it to galactic latitude and longitude. And you see, here's the galaxy across and galaxy up and down. You can tell that the galaxy has very bright objects right in the center of it, all the way across the center. And this big blotch right here is actually what I can't see. That's southern hemisphere. So you'll see that in most of the data from northern hemisphere astronomers because they can't look down south. And so I'd expect one of my southern astronomer buddies to go help me fill that in. If I plot this stuff with the same data with measurement of the velocity, I can actually plot it and see different other aspects of, and it's called radial velocity against galactic longitude. I can plot that. And this was very important for our team because we actually reproduced this picture that was done, I believe, by Harvard astronomers, and we were able to do it with our little Colorado Springs dishes. Now back to our SuperSID. When the August 21st and 2017, everybody remembers the eclipse that went over North America. Well, it's interesting that the SuperSID acts very much like the signal in the nighttime goes up and the signal in the daytime goes down. Well, what's an eclipse? An eclipse is like a night-day transition. So I actually did an experiment where I predicted that the signal would go up in the middle of the eclipse and then go down. And there's the actual signal of the eclipse. So it did. So we're very happy about that, the fact that we actually saw the eclipse with our little SuperSID system. Now, when you get to big flares, it goes from very low signal, an A flare, a B flare, a C flare, and then it goes to an M, an X, or excuse me, an M and an X flare. An X flare is the highest. And so on September 7th, 2017, we had a series of flares. And this is an example of an X 1.3 flare. And you could see it go straight up. And then what happens is that it ionizes the ionosphere. You get this real distinct bounce. And then over time, it starts to degrade. And then it doesn't reflect as much. And so they call it a shark fin. It sort of degrades and it sort of comes down nice and smoothly like this. So that's a characteristics of a flare. They go straight up and then comes down to a shark fin. So here as I got an X 1.3, and by the way, it only goes to X9, and then an M 3.9. So an M, so the second highest level. Here, I was really proud of this, but September 10th, we got an X 8.5. And remember, it only goes to X9. And this actually covered the entire day before it actually cleaned up. So this is, full X flare hit us, and that's hit the Earth, and then it took all day for it to come down to almost normal again. So this is with a simple system that costs less than $30 that you could put in your backyard. And I've had mine in my backyard for about 5 years now. and this is the kind of stuff you can get. Talking before about interferometers, the big interferometer groups, and this is the interferometers at very large array in New Mexico. This is the Atacama large millimeter submillimeter array called ALMA. This is in Chile. The European very long baseline interferometer is all over Europe. You can see where all those guys are. And then the Australian telescope compact array is in Australia. That one of the keys of interferometry, these big dishes, now this is the real professional big dishes, is that the farther away you can get the dishes, the real tighter you can see in the sky, and you can see smaller objects. If everybody remembers the just last year when they saw the black hole, and it was an M87, they were using a similar to the European Very Long Baseline for interferometer, but they were using antennas all over the Earth, including Antarctica, to get the very long distances, and they filled them in with antennas in between, and they were able to get very good resolution where they can see this black hole on M87. And that became the first ever black hole ever observed by an astronomer in real optics. And what they were not looking at the actual black hole, but they were looking at the bright object, the bright material around it that's superheated. They can see that, and then basically there's a shadow in between where the black hole is, where there's no light coming out. So they were able to see that very well. And that was done with radio astronomy, using a bigger version of these that we're seeing on the screen here. We did visit I've been to the Very Large Array down in New Mexico. They actually use this big tractor they put these antennas. This is actually one antenna in the barn, and they put it on this tractor and they move it to the different locations there. This is actually in its compact form. When it's at farthest out, it goes like almost 26 kilometers from the center. So they move these things in and out to get different resolutions over the year. This is an example of one of my hobbies in our group's hobbies is to take the data from these large antenna systems. They have archives, and process them. The actual professor who actually does the observing, processes them, writes a paper, but then the raw data from the observation is left in an archive for different public to use. So one of our things is to grab these archive data and process them and see if we can reproduce the results of these professors. And this is an example of a binary black hole. So two supermassive black holes, which a supermassive black hole is a black hole that's 1 million times or more bigger than the sun. And then normally in the center of galaxies, and this is one where there's two supermassive black holes actually rotating around each other. And you can see that. Very cool result there. This is our black hole in the center of the galaxy, Sagittarius A star. This is an example of what they can see with that. Now, this isn't as good as our black hole picture. This is actually the material around it you're seeing, not the actual black hole. You're seeing all the hot material and all the different stars in between. So it gives you a signal of a signal strength there, but the actual center is very small, and we can't see that with the current. This is the ALMA, almost too small to see the black hole itself. We can actually see asteroids. So the Juno asteroid, they saw that with the signal. M100 is a spiral galaxy, so much like the Milky Way is a spiral galaxy. Of course, we don't see it in that form because we're seeing it edge on, but we're able to see this one here is a nice side picture, or M100 is a nice, beautiful picture of a spiral sideways. and we can actually see that. Okay, and there's a protoplanetary disk, and it's Alpha Centauri. I was going to get a little pulsar astronomy. That's what I started with. The pulsar astronomy, first pulsars were found by Jocelyn Bell and Anthony Hewish in 1967. Basically, they were seeing a blip in their signals. They actually thought it was a something on Earth because it was too regular to be. They thought to be natural. They thought it was some man-made signal, and they even if it wasn't man-made because it was far away, then they thought, oh, maybe it's little green men. So they actually labeled it LGM for little green men at first. The let me see if I get this running here. Okay, so a pulsar, from our perspective, is rotating like a lighthouse, and it does these pulses as it rotates, and that's what we're seeing with the pulsar. So what's a pulsar made of? It's got an inner core and outer core. It's got a crust, and it's made out of neutrons. So it's very tightly packed neutrons. So it's so dense. It's the next thing denser, just not dense enough to be a black hole, but it's the next densest thing object in space. And they're only about 12 kilometers wide. They're not very big, about the size of a small city. So they're very dense. They're saying a teaspoon is about 1 billion tons or something like that of this material. They're located all over the Milky Way. And so there's lots of locations to look them at. They're normally formed with very, very fast speed. The period is how fast it turns around. It rotates once, and they're normally, this is period versus the slowing down. So if we just look at the period side, the Crab pulsar is the Crab Nebula, and that was just formed in recorded history, and it starts very fast. So period is very fast, and then it slowly slows down over millions of years, and it slows down to where it's called the graveyard. If it's with another object, like there's a binary one, sometimes it starts taking the material from its neighbor and starts speeding up, and it'll end up back down here and speeds up and it turns back on and speeds up, and it's called a millisecond pulsar. There's one other thing that we use in pulsars, and that's called dispersion measure. And because this is such a precise signal, pulsars are very precise in time, we can actually determine that at a high frequency, when the signal arrives, and then a low frequency when the signal arrives. And dispersion measure is at a high frequency will arrive sooner through material in space than a lower frequency. And depending on the difference in time that we receive them, we can determine how dense the material is in between the object and us. And so this is an example of dispersion measure, which is one of the key things we use to determine we got a pulsar. Here's my little pulsar observing team. So this was one of the pride things we're doing this year is trying to get a pulsar, and we managed to get 13 pulsars this year. We actually produced a pulsar simulator that actually produced a pulsar and received the data, so we can actually test our systems out. This is our first one of our first pulsars. This is the two peaks. And then you can actually see this is time and phase. So basically you can see the signal coming down here that we got a pulsar. And this is actually bandwidth. So you see the frequencies were at 418 millihertz or megahertz. We received that, but you can see that the pulsar was across the whole thing. And our dispersion measure is basically says where we were in the earth, on the Earth. So that's an example of a good pulsar reception. Then we can analyze it. The software allows us to analyze it. So this is an Excel analysis, and we can actually determine all the different aspects of this pulsar, its period, its pulse width, various other good data on that. Anyway, the Deep Space Exploration Society is always looking for members, and anybody in town, school-age children to adults. We've got, saying I'm the youngest guy. We have multiple 80-year-olds on this thing that are can race me anytime. They're faster than I am. So very all age groups. Whether you have any experience in astronomy or radio, that's okay. We're taking, we basically are training everybody to do everything. And if you have any other skills like carpentry, things like that, at our site, we're always looking for people that have skills that could do stuff. And the sister organization is the Society of Amateur Radio Astronomers. It's sort of like the international version of our group. And so you go to that, you can also see what the international version looks like. Okay, any questions? Okay, well, I thank you very much, everybody, and feel free to go to our website, and we'll be happy to talk to you. Thank you very much.